Okay, in this next video, we're going to talk about the non-homogeneous case, all right, and discuss the method of undetermined coefficients and the steps associated to solving second-order linear constant coefficient non-homogeneous differential equations. Again, what makes them non-homogeneous is what we call the forcing function on the right side here, which I'm underlining in green, g of t. Again, we call that the forcing function if you're thinking about an application like a spring mass system or an RLC circuit that corresponds to some kind of external force. Alright, so let's go through the steps and then we'll hopefully get to an example after that. Alright, so the first step we're going to do is solve the associated homogeneous equation. Alright, so you're making the right hand side 0 and then solving that. Alright, based on our previous work. Alright, and we saw in our previous video then your general solution is going to be a linear combination of exponentials or possibly exponential times trigs or maybe exponentials times t. Alright, that's what it's always going to look like there. Alright, and we're going to denote just notationally, we're going to denote the general solution of the homogeneous equation by y sub h. Okay, so that's something we're going to take care of pretty quickly. And again, we're going to do that by plugging in y equals e to the st, looking at the corresponding characteristic equation, which would be s squared plus ps plus q equals 0, solving that quadratic equation. And again, that either has two solutions or complex solutions, two real solutions, complex solutions, or possibly a repeated root. Okay, we've talked about that before. All right, so that's step one. We knocked that out. And then this is the new step. And what we have to do is we're going to find what we call a particular solution of the non-homogeneous problem. And again, up above here, when I have the equation, we call that NH for non-homogeneous. And we want to find some solution to that equation. And we're going to say how that's going to be done here in a moment, and we're going to denote that solution by y sub p. Okay, so the p here stands for particular solution. The h up above stands for the solution, the general solution to the homogeneous, the associated homogeneous equation. All right, so here's the breakdown for step 2. All right, again, I'm just going to rewrite the equation here. Again, we're looking at this kind of second order equation, y double prime plus say some number times y prime plus some other number times y equals g of t. The right hand side function g of t is going to dictate the types of solutions that we're going to be able to guess at. Alright, so we're going to find a particular solution by guessing the form of a solution up to an undetermined constant coefficient. Alright, and then plugging that guess into the differential equation to then determine what that coefficient actually is. That's why that was called the method of undetermined coefficients. Alright, and we're going to get to some of the options below here. But again, it all depends on that right hand side function. Alright, and I've got some of the options we're going to see. If the right hand side function is, say, an exponential, like I've got here in the first, I'm just going to point to where I'm at here, in the first column of this table, if it's say some exponential like e to the at, then what we're going to do is we're going to guess capital A, or just some other constant. Some textbooks or videos might use alpha, just some number, and I'm calling it capital A times e to the at. So again, in this case, we would let y sub p be a times e to the at. Then what we would do is take a first derivative, take a second derivative, plug it into the differential equation to figure out what that number, capital A, is. That's our undetermined coefficient. So if the right side's an exponential, we guess an exponential. If the right side's a constant, we're going to guess a constant. If the right side's a linear expression in t, linear function of t, we're going to guess a linear function of t, where we'd have at plus b. If it was a quadratic polynomial, we'd guess a quadratic polynomial. Okay, now it's going to turn out that if we have a cosine or a sine as our forcing function on the right hand side, then what we're going to do there is we're going to guess a linear combination. So in this case, if we have cosine or sine of, I'm calling it omega t, that's our number in front of t there, then we have to guess, and I've got a bit of a typo here, this should have been not a here, this should have been, and I'm just going to fix it here, this should have been cosine of omega t plus b times sine of omega t. Okay, so that should have been b. So again, instead of their a there, capital B. All right, so a linear combination of sine and cosine. We can't just have one or the other, because again, we would take a first derivative of cosine, we would get negative sine. Then a second derivative, we get back to cosine, again, we have the second derivative being negative sine and vice versa. The first and second derivative of sine or cosine, respectively, involves the other one. Okay, so what we would need there is a linear combination of both. You can't get away with just one or the other. All right, so that's what we're typically going to see there. All right, a couple comments to follow that in the next couple of bullets. If your first guess doesn't work, and that might be the case if the right-hand side function g of t is a combination of solutions of the homogeneous equation, then what we have to do is just take that first guess and multiply it by t. All right, so just as an example, I'm just going to write one down here. Let's suppose we guess, and we called y sub p, say e to the 3t. And if that guess didn't work, and we'll see this in some of the examples, then we would modify that as a second guess to get t, whoops, we'd have a constant coefficient in the front here, a times e to the 3t. Then what we would do here is we would modify our guess by saying, all right, it's going to be a times t e to the 3t power. All right, that would be if our right-hand side function was, say, something involving e to the 3t. All right, and what multiplying by t does, it has the effect of shifting the derivative to allow the unknown coefficients to be determined. All right, if that doesn't work, at worst, for second order equations, you'd have to multiply by t again, so you'd be multiplying your initial guess by t squared. All right, last comment would be that if g of t is a linear combination of two or more of these types, then what we would do is take our guess, our particular solution guess, to be a linear combination of these. All right, I've got an example down below here. So for instance, if we had a right-hand side function to be a linear function plus an exponential, what would you guess as your particular solution? You would guess a linear function plus an exponential. Okay, again, linear combination of the two types. All right, so that's the key step to this. All right, so again, what we're going to do is, depending on the right-hand side function, depending on the forcing function g of t, if we're going to guess a particular form or guess the form of a particular solution, plug it into the differential equation, and then determine what that coefficient would actually, coefficient or coefficients, if you have more than one, actually have to be. All right, and we're going to see some examples of this process in a minute here. All right, and then the last step is that we're going to just add the results together. So step 3 is pretty easy. Step 1 and 2 is where the work is. What is the general solution of the non-homogeneous equation we have at the top of the page here? It's adding our results from step 1 and step 2. So you take the general solution to the homogeneous problem plus the particular solution that you found. That will be the general solution of the non-homogeneous problem. So you could use that to solve any initial value problem. All right, I think what I'm going to do is we'll do an example in the next video. Let me just talk about some of the offshoots of the method of undetermined coefficients. If we look at the mass spring system or even an RLC circuit, they can be modeled by second order linear constant coefficient differential equations. So they fit sort of into the mold we're talking about here. Now, if we were dividing through by the mass or by the inductance in these equations, we would get a similar looking equation to what we have down below. All right, and we're going to see in the rest of chapter 4 here, we're going to break these into two types, either damped or undamped harmonic oscillators. If we're talking about a damped harmonic oscillator, then when we look at the solution, all right, the solution y of t, which will be a sum of the homogeneous plus the particular solution, if there's damping in there, then what we're going to find out is that the damping is going to make the what we call the natural response approach 0 as t goes to infinity, and therefore in the end, all right, the solution as t gets large will only be determined by the particular solution. So what we're saying here is that the solution is going to be close to the particular solution for large values of t if we're talking about friction being in there, or resistance if we're talking about the RLC circuit. In the undamped case, that means there's no friction between the block and the table, or there's no resistance in the wire. In that case, the natural response will not be damped out, and therefore the end behavior depends on a couple of factors, one of them being the forcing function that we have in there. Okay, so in the next video we're going to look at an example, but let's just review the steps here, and then we'll get to it. All right, so first step being, right, solve the associated homogeneous equation. So make the right-hand side 0. Determine the general solution, all right, based off of our previous work. Step 2, find the particular solution by guessing the form of a particular solution up to an undetermined constant coefficient, or possibly more than one, and then plug that into the differential equation and figure out what those constants actually are, and then lastly add your results.